Hi guys, welcome back. Hope you're doing well. Those of you who are in class, hopefully I will see you tomorrow. I have no idea, but I will know later today and I'll keep you informed. All right, so interpreting graphs. Okay, there's really no new information today. It's just a matter of practicing this type of question, okay? So I'm going to be giving you graphs that are either the original function or the derivative graph, and you're going to be asked all of these questions, okay? So first, this is where you really need to know your definitions or your justifications really well, or you'll get totally confused, okay? So if you don't already have these notes where you can see them and see them quickly, this is stuff you should already know cold. You need this all year anyway. I think you already know this, but if not, take a picture of it, print it out, whatever you need to do. These are all your first derivative issues, okay? Remember, critical points do not have to change sign, okay? If they do change sign, then they become maximums and minimums, okay? All right, next is second derivative issues. Second derivative issues are basically concavity and inflection points. Inflection points do have to change sign. Now, the alternate definition of concave up and concave down. Hold on a second. The alternate definition for concave up and concave down. This is my go-to, second derivative positive. But the other definition is sometimes helpful also. So think of the word increasing is a first derivative issue. So this is kind of like a derivative of a derivative. And that's why it's the same as second derivative positive. This is a first derivative issue, so it's a derivative of a derivative. And that's the same as second derivative negative. Okay, you need to know all of this. Should already know all of this. Cold, all right? All right, the other thing that you should already know, the difference between average rate of change and instantaneous rate of change. Average rate of change is basically your estimated derivative or your algebra 1 slope. And it's the slope of the secant connecting the two endpoints on that graph. Okay, so whatever the endpoints are, you connect those. Okay, so the average rate of change. Instantaneous rate of change, or honestly, even if they don't say the word instantaneous, if they just say rate of change, or rate for crying out loud, that means actual derivative. Okay, so we have average rate of change, which is your algebra 1 formula for slope, and instantaneous rate of change. Slope of secant versus slope of tangent. All right, that's all the stuff you're supposed to already know, but that's the stuff that will be applied into interpreting graphs. All right, here we go. You got to pay real close attention to the title of the graph. If it's the original function that they've given you, then all of these questions are stupid easy and you already know how to do it. So if the title is the original function, then this is quick, stupid review, and you should know how to do this on the fly. Okay, critical points, that would be first derivative is 0, and that's basically slope of 0 here, here, and here. Okay, out of those critical points come your maxes and mins. So this guy is a max. And these two are mins. Duh, we know that. Easy. Okay? F of x increasing. That's where it's going uphill. Duh. This would be f of x increasing, and this is f of x increasing. F of x decreasing would be blah, blah. Okay? Now, just a reminder of how you write those answers. Let's go back to part C. F of x increasing, the blue section. I would write that as -3 to not quite 0. So we don't know exactly what that point is, but I can see it's not 0. So you should give an estimate, approximately negative 0.1 or 0.2. Doesn't really matter, but it shouldn't be 0, okay? And this region over here should be from 3 to, now honestly I intended this to have arrows, but I didn't graph it with arrows, so we're going to assume it, but 3 to infinity, unless I told you that the graph closed at a certain spot, okay? And be warned, on my worksheet, my answers, I also can't remember if I forgot to add arrows and stuff, so that might change your endpoints. Technically, if it has no arrows, you should end the graph, and I maybe should have said from 3 to 4, that last spot. So it depends on the directions and whether or not there's arrows. I'm just going to cheat and add arrows now because I know I meant them. All right, inflection points. Let me clear off this mess I got going here. Inflection points are where concavity changes, and that's an estimate if I've given you the original function. So this graph appears to be concave up here, concave up here, and concave down here-ish. But where exactly does that concavity change? Well, that is we can only estimate it on the original function. So I'd say the inflection point is approximately here and approximately there. Okay, it's an estimate though. So inflection point at approximately negative 1.9 and approximately 1.2 or something, okay? However, whatever you do estimate them to be, make sure you use the same answer when you're doing part F and part G, and that you use that same point. Concave up would be the area in red, concave down, area in blue, okay? All right, H and I. F of x increasing, remember that's a derivative of a derivative, so that's second derivative, positive, and that's really the exact same thing as part F, concave up. It's all the stuff in red, okay? And part I, F prime decreasing. Notice that that's not, H and I are not the same as C and D, okay? So this one is a trick. It's really a second derivative question. Derivative of derivative, that's the same as second derivative negative. That's the same as concave down. It's the same as letter G. It's this region right here. Okay? All right, so now we're going to switch it. And basically, instead of being given the original function, I'm going to give you the graph of the derivative. Okay, this is now already a derivative graph, but all of the questions I ask you are going to be about the original function. So make a big deal out of noting that this is the derivative function, not the original function, okay? And I changed it to an H just because we get into the habit of always using H in our F in our justifications. Okay, where does the graph of H have critical points? Whenever they don't give you the original function, you really want to write your justification or your definition first, okay? So critical points. The definition of a critical point would be where the derivative is 0 or undefined. Now, I don't need to state undefined if there are no undefined issues. Okay, so if this is the derivative graph, and I'm looking for where this derivative is 0, then I'm looking for where its height is 0. Well, that would be, height of 0 would be here, oops, here, here, and here. Those are my critical points, even though it doesn't look like it. Okay? Now, out of those critical points come my maxes and mins. Okay? So when I say positive, I mean a height. I want you to think height is positive. Height is negative. Height is 0. Okay? I'm looking for where the derivative changes from positive to negative or negative to positive. Okay, well, positive is all of this stuff up here, height of positive. Negative would be down here. So these are my critical points, the red dots. If they also change from positive to negative or negative to positive, then they become maxes or mins. So this guy right here, this goes from a height that's positive to negative. If my derivative goes positive to negative, then that becomes an uphill, downhill. That is a max. This one's a max. Okay? This one over here, the derivative went from below to above. So it changed from negative to positive. If it goes negative to positive, downhill, uphill, that is a min. This critical point over here didn't change signs. It went positive, positive. So you're not looking at slope. You're looking at height. Okay? So this is a max, this is a min, and this is just a critical point. All right, so rewind if you need to, watch that again. That's a little bit tricky, but here's the short of it. If your justification or definition if this guy is the same as the title, they're both one derivative, or they're both the first derivative, then you want to look at height is 0 and changes from positive to negative. Okay? All right, let me show you another one. Where is the graph of h increasing? Well, again, write your justification first. H increasing means h prime is positive. Write the justification first. All right, well, this is a graph of h prime. It matches. The justification and the title are the same, so we think height is positive. Okay, well, height positive is going to be everything above the x-axis, all of this, 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 and this. And again, I'm going to assume arrows. So how do we write that answer? Well, it's all of that stuff in red. I wish I had changed it to negative, by the way. It would have been quicker. Everything there in red. But at this spot right here, most textbooks would not include that as being positive because technically it's not positive there, it's 0, which is neither positive or negative. So my final answer would be negative infinity up to negative 3, and then start again at negative 3 and go all the way over to 2, and then jump and go from whatever you think this is, like 3.5 to infinity. Okay? Now, would I mark it wrong if you just called that one big chunk negative infinity to 2? Probably not, but it's technically not quite right to do that. All right, so again, main idea, if your justification and the title of the graph are the same, then I want you to think in your mind, height is whatever this says, positive. Okay? All right, let's try another one. Inflection points, okay? So I'm going to write my definition for an inflection point. Second derivative is 0 and changes signs. Okay? So second derivative is my justification. But this title is first derivative. So we're looking for a second derivative issue on a first derivative graph. If you're one derivative away, then you look at slope. That's the same as being given the original function and being asked a first derivative question. We look at slope. Okay, so my justification is a second derivative, but the title is a first derivative. If you're one derivative away, think slope. So you can write it, but you have to write this formal justification. But what it means in your mind is slope is 0 and changes signs. Okay, but you can't really actually use that in your formal justification. It won't count. So, but that's what you're thinking. All right, slope of 0 would be here, here, and here. Now I need to make sure that the slope changes signs. Slope goes downhill, uphill, yep, that counts. Uphill, downhill, yep, that counts. Downhill, uphill, yep, that counts. So my inflection points would be at an x-coordinate of approximately -3, -0.2, and 2.9 or 3, I can't really tell. Okay? Those are your inflection points. So let's summarize everything again one more time so far. If your definition is the same as the title, think height. Okay? You're looking at the height of the graph. If your justification is one derivative away from the title, think slope. Okay, let's do another one. Okay, concave down, write your justification. Second derivative, sorry, hold on. We're looking for second derivative is negative. Okay, again, that we are one derivative away from the title. So we're looking at slope is negative. So where do we have a negative slope? Here and here. That's actually concave down, even though it doesn't look like it, because this is not the graph of the original function. This is the graph of the derivative of the function. So you can't trust your eyeballs. As soon as the title is no longer the original function, you can't trust your eyeballs. A max doesn't look like a max. A min doesn't look like a min. You have to trust your justifications, okay? So the solution for that one should have been negative infinity to negative 3 and negative 0.2 to 1.9, whatever you used before, use the same values. All right, that's everything. That's the whole lesson. So I'm just going to do one more to see if, make sure you understood, okay? Nope, I lied. I forgot to go over average rate of change. Okay, so before I go over all of that other stuff, let me do the new question. This one, average rate of change. Okay, where does the average rate of change equal the instantaneous rate of change on the interval from negative 2 to 3? First, go to your graph at negative 2 and put a point right there. Go to your graph at 3 and put a point. I missed it right there-ish, okay? Connect those two with a straight line. That's my average rate of change, okay? They want to know, where does that equal my instantaneous rate of change? So where's the slope of that secant? The same as the slope of the tangent? And I'd say it's approximately right there maybe. That looks about right. So now you it's an estimate. So now you got to give like that point right there, the x coordinate. So I'd say at approximately 1.1. Okay, that's how you do that one. Now, do you remember the name of the theorem that really is asking about? Estimated derivative equals actual derivative. FYI, that's really the MVT, mean value theorem. Okay, you don't really need to know that right now, but you are supposed to know that. Okay, all right, now reviewing all the other stuff if you need to. If you don't, then fast forward past this, okay? Because I think these questions are easy because the original function is given. The tricky ones are when I give you a derivative graph. Okay, whereas f of x increasing, slope positive, here. It looks increasing. As long as you have the original function, you can trust your eyeballs. Decreasing, part B would be here. Critical points. Doing, doing, slope of 0. Oh, I missed that one. Try again. Boing. There we go. Those are my critical points. Out of those critical points, this one's a max, this one's a min. Okay, again, you can trust your eyeballs as long as the original function is given. All right, now let's look at part F. F prime increasing, that's derivative of a derivative. That means second derivative positive. So we're looking for concave up. Concave up would be approximately this, okay? Wherever you think that starts is an estimate. Inflection, or concave down would be the other stuff. All this is concave down, okay? Inflection point would be where it changes. So it's an estimate, but I'd say right there, okay? At approximately negative 0.8. All right, so it's easy as long as the original function is given. The only tricky one is maybe part F. All right, now let's do, if I give you the derivative graph, I would hit pause and try to do these on your own. Okay, I'm not going to do all of these. I'll just do like every other one. So, when is f of x increasing? When f prime is positive. Okay. Well, the definition and the title are the same, so I'm looking for height positive. That would be all of this and this. Okay, that's f of x increasing. Now, does it look like it's increasing everywhere? No, and remember, that's because you cannot trust your eyeballs when they give you the derivative graph. You have to trust the definition. So f prime positive, and this is an f prime graph. That means height is positive. Okay? I'm going to skip to part C. Critical points. F prime is 0 or undefined. This is an f prime definition on an f prime graph, so height is 0. That looks like x-intercepts. Not your typical looking critical points. Out of those critical points are my maxes and mins. Okay, and the first one, this goes from below to above. So this one's going from negative to positive, and this one's going negative to positive. So if your slope goes from negative to positive, that is a min. These two are mins. The other one goes positive to negative. That one's a max. Okay, let me clean it all up now. Let's do part F, concave up. Concave up would be second derivative is positive. Okay, second derivative definition on a first derivative graph. If you're one derivative away, think slope. So you're going to think slope is positive. Okay, so slope positive would be, here and here. So it doesn't look concave up because you can't trust your eyeballs. So for part F, concave up would be negative infinity to approximately negative 2.8 and approximately 1.4-ish to infinity, again assuming arrows. Okay? All right, last one, inflection point, part H. Inflection point would be second derivative is 0 and changes signs. You have to say that part, okay? And changes signs. Okay, so second derivative is my justification on a first derivative graph. One derivative away, so you're going to think slope changes signs. Well, slope changes signs from positive to negative, so that's here. And slope changes signs from downhill to uphill, that's going to be here. So my maxes and mins are actually the inflection points. So negative approximately, x is approximately negative 2.8 and approximately 1.2. Okay, so to summarize one more time, if I give you the derivative graph instead of the original function, don't trust your eyeballs, trust the definitions, and write the definition first. Trust me. All right, good luck, guys. I gave the answers. I've worked them all out, so make sure you're checking as you go, okay? Good luck. Hope you're doing well.